How a transformer works. Hello everyone. Today, we are going to discuss how a transformer works. Reasons for introduction of transformers. The need for transformers arose due to the losses that occurred during electricity transmission over long distances from the locations of electricity generation to the locations of its consumption. Reducing these losses requires increasing the voltage. The longer the transmission line and the greater the transmitted electrical power, the higher the voltage should be. However, as a rule, consumers should not be connected to the high voltage line. Therefore, the voltage must be stepped down at the end of the line. Transformers are used to first step up and then step down the voltage. Thus, a transformer is a device that allows converting an alternating current of one voltage into an alternating current of other voltage without changing the frequency. Physical principles underlying the transformer operation. The operation principle of the simplest transformer is based on the physical phenomenon of electromagnetic induction. This phenomenon consists in the fact that if there is a closed conducting loop in a magnetic field that contains no sources of current, then an electric current begins to flow in the loop when the magnetic field changes. The occurrence of a current indicates the emergence of an electromotive force, EMF. In other words, an electric field that ensures a closed motion of electric charges. Thus, if we have a source of variable EMF and a coil connected to this source and comprising a certain number of turns, then we can obtain an electromagnetic field. The lines of force of the electromagnetic field created by a coil will look as shown in the figure now. Due to the variable nature of the current flowing through the coil, the electromagnetic field will also be variable. It means that its lines of force will fluctuate. Now let's take a magnetic core made of ferromagnetic material and a second coil. When the current passes through the primary winding, a magnetic flux is formed inside the magnetic core and will circulate through the magnetic core and penetrate all the turns of not only the primary, but also the secondary coil. An explanation of how exactly a transformer converts an alternating current of one voltage into an alternating current of other voltage will be given using mathematical formulas. According to the phenomenon of electromagnetic induction, EMF is induced on the ends of the second coil and will comprise the sums of the EMFs which are induced in each particular turn. It means the following. E2 is equal to E2 multiplied by N2, or E2 is equal to the ratio E2 and N2, where N2 is the number of the secondary winding turns. Whereas the same magnetic flux penetrates both the primary and the secondary winding, the EMF on the turns will be equal for the primary and secondary windings. E1 is equal to E2. Therefore, the EMF on the primary winding turn will equal the ratio of the total EMF and the number of turns. E1 is equal to the ratio E1 and N1. Whereas the left-hand members of the equations are equal, we can equate the right-hand members thereof. The ratio E2 and N2 is equal to the ratio E1 and N1. Having expressed E2, we will obtain E2 is equal to E1 multiplied by the ratio N2 and N1. Thus, if we reduce the number of the secondary winding turns capital N2, this will allow decreasing the output voltage. When the number of the secondary winding turns is increased, the output voltage will increase by contrast. That is how a single-phase transformer works. In simplified form, a three-phase transformer can be represented as a device consisting of three single-phase transformers with a slightly different configuration of windings where the primary and secondary windings are embedded relative to each other. Transformer windings connection diagrams. Various diagrams can be used to connect the windings of three-phase transformers. However, the power systems do not require many connection diagrams for practical purposes. Therefore, Y and delta connection diagrams are mainly used in both step-up and step-down power transformers. In order to obtain a Y connection, the ends or starts of the windings of three phases should be connected together. A delta connection can be obtained if the end of phase A, point X, is connected with the start of phase C, the end of phase C, point Z, is connected with the start of phase B, and the end of phase B, point Y, is connected with the start of phase A. A Y connection of higher voltage windings with the neutral available is applied to high voltage transformers, and a delta connection is applied to lower voltage windings. It means that 4 wires can be led from such a transformer, 3 power wires and 1 neutral wire. Transformer design. High voltage insulators are installed in places where a live conductor shall pass through the grounded metal housing of the transformer. Insulators ensure mechanical fastening and insulation of the current carrying conductor from adjacent conductors. A magnetic core of the transformer consists of rods on which the windings are located, and a yoke connecting the rods into a common magnetic circuit. The magnetic core is made from thin insulated steel plates. Laminated assembly is used for improving the performance of plated magnetic cores. Its principle is based on clear distribution of layers and creation of equal gaps therein inside the rod and yoke in such a way that all the created cavities are filled with minimum jointing during assembly. At the same time, the plates of the rod and the yoke are intertwined with one another, forming a robust and rigid structure. The laminated structure of the magnetic core allows reducing the losses that occur when eddy currents arise. Furthermore, losses occur in the transformer when power is transmitted from the primary to the secondary winding. These losses are dissipated as heat. Therefore, the windings are placed in insulating oil to avoid overheating. Heat is transferred from the oil to the air by natural convection through a radiator. Absorbing the heat, the transformer tank oil heats up and concurrently experiences volumetric expansion, which means an increase in volume. Fluctuations in the oil volume are compensated by means of an expansion tank. If you liked this video, and if you consider it informative and helpful, click on the like button, recommend it to your friends, and subscribe to our channel.